suppose we have any number 5, we have to subtract 5 minus 7. So it's become difficult for us to subtract 5 from 7 from ordinary method. So we use 2s complement to subtract number from any number. It is basically used for the subtraction purpose. Also, one of the main advantage of 2s complement is that the range of number is from minus 2 to the power n minus 1 to 2 to the power n minus 1 minus 1. But that's not the case in the signed presentation. In signed notation number, the range is minus 2 to the power n minus 1 minus 1 to 2 to the power n minus 1 minus 1. Here the advantage of this is that the range is high, and also in signed notation. So what we do in signed notation, when the number is suppose we have any binary number in signed notation, when we put 1, it means that the number is positive. When we put 0 in the last, it denotes that the number is positive. So for 000 binary number, it can be positive or negative. So we have to give two values, plus 0 and minus 0. So 0 has two values because it is both positive and negative. So that's why the range is 1 less in signed notation, and 2s complement the range is 1 high. So that is very important difference. And also in 2s complement, the range is high. It is basically used for the subtraction purpose. Okay. So suppose we have to subtract 5 from, suppose we have any binary number 0 1 1 0 1 0. How we convert it into 2s complement? To convert any binary number into 2s complement, the first step we have to do is we have to take 1s complement of that number. How we take 1s complement? We toggle every number 0 to 1, 1 to 0, 1 to 0, 0 to 1, 1 to 0, 0 to 1. And now we have to add 1 in that 1s complement to get 2s complement. 0 1 1 1 1 1 1 1. These are the 2s complement of the number. So it is basically a negative number which is used for the subtraction purpose. Suppose we have to subtract 5 minus 7. So what is the value of 5? 0 1 0 1. It is 5, and for 7 1 1 1. So it's very complicated to subtract 101 111 from 101. So for that purpose, we will first convert it into 2s complement. For 2s complement, we will take the 1s complement 0 0 0, and we add 1. It becomes 0 0 1, and now we can add 101 to that number 110 1 1. So we can subtract easily by using 2s complement. Any doubt? And also suppose we have this number. Yeah, one shortcut method to convert the binary number into 2s complement is that we will write the number as it is until we get 1. We will start from the LSB. LSB is what? 0 0. We will write the same until we get 1. Here we get 1. Now I will write the number as it is until we get 1 from LSB, and after that we toggle every number. We convert 0 to 1, 1 to 0, 1 to 0, 0 to 1. So in this way, we get 2s complement directly from a number. 0 1 0 1. 1 0 1 0 0 1. So here in both cases we see that the 2's complement is 7. So in this way we can directly convert binary number into 2's complement. Any doubt? What is BCD number? Can anyone tell me what is BCD number? BCD number is a 4-bit number which is used to denote number from 0 to 9. Suppose we have number 27, we have to write BCD number. We have to write 4-bit number of 2 and 4-bit number of 7, such that the number is between 0 to 7. So 2 can be written as in 4-bit 0 0 1 0. It is BCD number of 2. And for 7, we will write 0 1 1 1. So the number is a BCD number is a 4-bit number which is in between from 0 to 9, and it is denoted by 4-bit number. So in this way we can write 27 into BCD number as 0 0 1 0 and 0 1 1 1. In this way we can write any number in the BCD form. So the main difference between the normal gray code, XS3 code, and binary code is BCD code is that it is weighted code, because for every number we have unique solution of 8421 implementation. For every number we have unique implementation of 8421 implementation, but it's not so in the other methods, because suppose we have to convert this number into decimal. We can't convert it because in decimal its value will change. So we cannot convert BCD number directly into binary number because it is weighted number. But for non-weighted number, we can convert it directly into the decimal or any other conversion, but it's not possible in the BCD number. Any doubt? What is weighted code? Weighted code, I have already discussed here that every position has its weight, and we have to add that number. I have already discussed 27. 2 have different value and 7 is different value. Here the 2 is 0010 and 7 is 0111. So every number has different weight, and every number is calculated according to the 8421 implementation of BCD number. So that is what the weighted code is, and in weighted code we cannot convert it into directly decimal or octal on or hexadecimal. But non-weighted number is not the same. Not non-weighted number, in this number conversion is possible, and the number is directly written into the decimal form, and conversion is possible at any point. XS3 code. The main advantage of XS3 code is that suppose we have any number 000, it is self-complementary. Self-complementary means to say that I will show you, demonstrate you with example. The access code of 000 is when we have to calculate access code of any binary number, we have just to add 3 in that number. We have to add 011 in that number. So it will become 011. The access code of 000 is 011. Suppose we have another number 011. The access code of this number is, we again add 3 in that number, and it will become 011. it will become 6. So the access code of 0 is 3, the access code of 3 is 6. But the point of notice is that when we convert 0, 1, 1, when we take 1's complement of that number, that is 1, 0, 0, the summation of 1, 0, 0 and 0, 1, 1 will always be 9. What is the value of 100? 6. 6 plus 3, 9. That's why it is self-complementary. The number of 1 is complement and the number itself is always 9. I've already discussed how to convert gray code into binary code. You have a question? We have in number 11001. You have to convert into binary code. Do it. Do it. I am giving you 5 minutes break. I will come back in 5 minutes. While you do this question, you can convert this number into binary code, and also I'm giving you one more question. Convert 101101. Convert it into gray code and convert this gray code into binary code. I will be back in 5 minutes.
Yes, sir. Audible, sir.
Yes, have you solved that question? Hello? Have you solved that question which I gave you? One. We have to convert 11001, that is gray code, into binary code. First, we write the same MSB as it is. The one we write the one as it is. The process of converting gray to binary is that we write the MSB as it is. Now we check that if the number is same, the next bit is same. That is 1 and 1 are same. Then we write 0. Again, we got 0. Now we compare it 0 with the next bit. If the number are same, that is not toggling, then we again write it at 0. Now we compare that number again with the next bit. If the number are same, then we again write it is at 0. Now we compare that bit from the next bit. Now we again compare 0 with 1, that the number is toggling, we write it as 1. Okay. And in that case, here the number is 1, we write MSB as it is. Now we compare these two numbers. The number is toggling, then we write 1. Then again the number is toggling, we write 1. Then again the number is same, we write 0. Again the number is toggling, we write 1. Again the number is toggling, we write 1. Number is same, we write 0. In this way we convert binary code to Greek code. Okay. Tell me which of the following gates is a universal gate? Am I audible? Hello? Anyone know what is a universal gate?
NAND, NOR, and NOT.
Okay. NAND and OR is used as the universal gate because every gate or every circuit in the world, that is the circuit used in the processor, higher processor, RISC, UART, or any circuit, that circuit can be implemented using NAND and NOR. Even when we use Verilog, the netlist that is generated, it only consists of NAND and NOR gate. NAND and NOR are universal because every gate can be implemented using NAND and NOR gate. That's why these both gate are universal gate. Now we have some important questions. These are generally asked in the interview, and every interview they will start with these questions. They will ask to implement AND gate, OR gate, NOR gate, NAND gate, or OR gate using 2 into 1 mux. So we will start with the first NOT gate. Okay. Is my screen visible?
Yeah.
What is the function of NOT gate? It just invert the number. What? So we have to make NOT gate, design NOT gate using 2 into 1 mux. Do you have any idea about mux? Hello? Do you have any? So what is, suppose we have two input I0 and I1, and we have select line S. What will be the output of the mux?
S bar I0 plus S I1.
Very good. S bar I0 plus S I1. Now we have to implement NOT gate using mux. We have an input A. When its value is 0, the output is 1. When its value is 1, the output is 0. Okay. So what will I do? We took select line A. Okay. The value of A is 0, the output is 1. So when the select line is A bar, that is 0, the output will be 1. When the value of A is A, that is 1, the select line will be 0. In this way, we can design a NOT gate. Y is equal to S bar. It means A bar into 1 plus A into 0 is equal to the value of I is, that is I0. I0 value is 1 or I1 value is 0. So it will be A bar. Any doubt?
No, sir.
We have no one has doubt in this. If you have doubt, you can ask, because from next one complicated circuit. So here we have taken A as a select line, and according to the truth table, when the value of A is 0, that is A bar, we have used 1. When the value of A is 1, we have used here 0. So here we have used the formula S bar I0 plus Si. That is, in place of select line, we have used A. A bar, what is the I0? 1 into 1 plus, in the place of S, we have used A. In the place of I1, we have used 0. So we can get A is equal to A bar using mux. Okay. Now the next question is, we have to implement 2 input AND gate using mux. How can I implement it? we have to first draw the truth table of AND gate. A, B, and output Y. 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, and 1. So we have to implement it using mux. So we can say that when the value of A is when the value of any of the input is 0, then the output is 0. And when the both A and B are 1, the output is 1. So I0, I1, left line, and output. So how will we implement this circuit? So we take B in place of select line, and when the value of, and we take here 0, and we take here A. Why you took so? I'm illustrating it. S bar I0 plus SI1. When we take B here, the output will be B bar into 0 plus, when we select line as B into A. So in this way, we can directly get the output AB. Why we took 0 here? Because we don't want B bar in the circuit. That's why, because in the formula of AND gate we have only AB, and we don't want B bar. So we have to make it 0 so that B bar term will automatically get cancelled. So we are taking only the term of B. And what is the formula of AND gate? A into B. So we will, according to that formula, this term will get 0, and this term will come out A into B. In that way, we can design A into AND gate using mux. You have to use some logic, and you can also do hit and trial method, because there is no specialized process to implement this. You have to just use your logic, how that you can reach to that formula. So we don't want B bar here, that's why we have made it 0. We want only AB. So when the select line is B, we have to multiply it with A according to the formula. That's why we have used 0 and A here. Any doubt?
Sir, in place of select line, can we use A? That means in select line.
Obviously, you can use A. You can do it in that way also. You can use A here.
Okay.
Again 0 here, because we don't want A bar, and B here. The output will be again AB.
Okay. So that is for AND gate. If it is OR gate, I can place 1 on the 0 section. Is it okay? That means.
Yeah. If it is OR gate.
Okay.
If it is OR gate, in OR gate, what is the output? Y is equal to A
Y
plus
equal
B.
to, yeah.
A plus B. So how will we implement it?
A plus B means, that means select line should be either.
Suppose we have taken B here, okay?
Okay.
B here,
So
and
that should be B complement should not be 0. That is 1. Okay. 1 is there. Okay. Next,
1 is
another
there,
signal is a A.
and another signal is A here.
Okay.
So
Yeah.
B bar A plus B, according to the associative formula, we can write it as A plus uh, A plus B into, sorry, when the equation is in the form of uh, when the equation is a form of uh, B bar A plus B, what can I do?
Into
We can write it as
B into 1 plus A.
B plus B bar into B plus A. That is from De Morgan's theorem. When the equation is a form of this, we can write it as B plus A into B plus B bar. B plus B bar is always 1. So we can write it as A plus B. And how can I implement it using truth table? When we use truth table,
Yes.
Truth table will be first one is a 0, remaining all will be 1.
we have 0, 1, 1, 1. Now, how can I implement it? Using truth table. When the value of A is 0, the value of B will define the value of output. Is it okay? When the value of A is 0, what will happen? The value of B will define the output. When the A is 0, when the B is 0, output is 0. B output follows the B when the value of A is 0. And the value of A is 1, the output always will be 1. That's the two case. Now, how will we implement it using mux? So, in mux, we have A bar. A bar means to say, when the value of A is 1, A bar will be 0. So, when the A bar is 0, the value when the value of A is 0, the value of B follows the output. And when the value of A is 1, the irrespective of B, the output will always be 1. So here in that case, okay, internet connection. My screen is visible.
Yeah, it is visible.
Yeah. So A, B, 0, 0, 0, 1, 1, 0, 1, 1. 0, 1, 1, 1. As I have told you that when the value of A is 0, output follows the B. Okay. In the first two cases, when the value of A is 1, the output always be 1. We can split it into two parts. Now, how will you implement it in by using mux? Okay.
Okay.
So when the value of A is 0, that is A bar case, B will follow the output. Okay. When the
Okay.
value of A is 1, that is in the case of when the select line is A, it will always be 1. So in that case, the value will be y is equal to A plus B. Are you getting what am I telling you? I have split
No.
it into two parts. We have used it as A bar. A bar. When we used it as A bar select line, the value of B follows the output. What will be the value of B? It will be the output. In the case of A bar, okay. When the select line is A bar, that is B. B will follow the output because it is selecting B. Okay. When the value of A is 1, that is I am selecting A. Then output will always be 1. We have given 1 here. So how will you justify it? S bar I naught plus S I1. Okay. But A bar I naught, that is B plus A. How can I write is A plus A bar into A plus B. That is A plus A bar value is 1 and A plus B is same as it is. So we get the value A plus. Are you getting? Hello?
Yeah, yeah. It is clear now. Yep. Hello.
So we have covered OR gate, AND gate, and okay, the next part I will do in the next lecture. We have some more important part that will take time too much. So I will continue the rest of the part in the next class.
Thank you, sir.